In 2016, an underwater robot descended into a flooded forest chasm in the Czech Republic. Its task? Find the bottom. So what does bottomless actually mean? This is not a story about supernatural lakes. It is a story about the places where the map ends first. But the numbers on the depth counter kept climbing. 330 feet, 660, nearly 1,000. The robot passed the deepest point a human diver had reached there and continued into water no person had ever seen. Its lights revealed pale rock, suspended particles, and an enormous flooded space that seemed to keep opening below it. Then, at 1,325 feet, the mission stopped. Not because the robot had landed on the floor, the cable had run out. The machine's reach, not geology, had defined the known depth. 6 years later, a more advanced robot returned. It had no tether, carried multiple sonar systems and cameras, and could build its own three-dimensional map while navigating in total darkness. It went deeper, and the cave still did not give up a final bottom. No lake is a tunnel through the center of Earth. But some bodies of water open into geological systems so deep, narrow, unstable, or complex that the bottom becomes surprisingly difficult to define. A rope can disappear into mud. Sonar can look into a side passage. A cable can snag on rock. Radio signals fade in water. And a robot can reach the limit of its navigation long before it reaches the end of the cave. In the mountains of Kabardino-Balkaria lies a lake called Cerik Kel, also known as the Lower Blue Lake. From the shore, it looks almost artificial, a compact basin of blue-green water surrounded by steep rock and forest. Even through severe winters, its temperature remains close to 48 degrees Fahrenheit. But its most interesting feature is not the color, it is the water budget. There is no large river pouring into Cerik Kel at the surface, yet water continuously flows out of it. A 2016 expedition estimated the daily discharge at roughly 18.5 million US gallons. If that much water leaves every day, something has to replace it. The answer is beneath the surface. Cerik Kel is part of a karst system. Karst forms where groundwater moves through soluble rock, especially limestone. Rain absorbs carbon dioxide from the air and soil, becoming weakly acidic. Over long periods, that water enlarges fractures into channels, channels into passages, and passages into caves. The result is a landscape with two drainage systems. One is visible, rivers, streams, and valleys. The other is hidden inside the rock. At Cerik Kel, expedition data indicated that water enters through numerous cracks and fractures rather than one dramatic underwater spring. The lake is not violating the water cycle. We simply cannot see most of its plumbing from the shore. And the plumbing is enormous. For years, the accepted depth was about 850 feet. Then researchers used dives, sonar, and a remotely operated vehicle to examine the geometry below the visible basin. They mapped previously unknown cavities, and in one of them, the vehicle reached 915 feet below the surface. The expedition reported that the passage appeared to continue, but visibility collapsed before it could be completely mapped. That distinction matters. 915 feet is a measured point. It is not proof of infinite depth. Beyond it lies an unconfirmed continuation, a question, not a number. At that measured depth, the pressure is roughly 410 pounds per square inch, about 28 times the pressure at the surface. Every housing, camera seal, connector, and light must survive that force. Meanwhile, the vehicle has to remain oriented in a space with no sunlight, no GPS, and few reliable visual landmarks. What looks like a quiet alpine lake is really an accessible window into a much larger groundwater machine. And that machine explains why a lake can release millions of gallons every day without a visible river feeding it. The word bottom sounds simple only because we imagine a bowl. In an ordinary lake, depth is the vertical distance from the surface to sediment or bedrock directly below. But a flooded cave is not a bowl. It can contain vertical shafts, shelves, collapsed blocks, sediment clouds, narrow restrictions, and horizontal tunnels. Drop a weighted line into that geometry and several things can happen. The weight may reach solid rock, or it may sink into soft sediment without producing a clear impact. It may land on a ledge that is not the deepest point. It may be pulled sideways by water movement, or the line may enter an inclined passage, leaving the person above convinced that the lake continues vertically when the cable is actually traveling at an angle. Modern sonar is far more powerful, but it also measures echoes, not certainty. Sound pulses spread through the water, reflect from surfaces, and return to a sensor. A multi-beam system sends many pulses at once, allowing software to reconstruct underwater geometry. But a narrow cave creates difficult echoes. Sound can bounce from multiple walls. A beam may enter a passage at a poor angle and fail to return clearly. And as distance increases, resolution falls. To produce a detailed map, the sonar has to move closer to the cave walls, exactly where navigation becomes more dangerous. This is why "we did not find the bottom" and "there is no bottom" are completely different statements. One describes the result of an expedition, the other makes a claim about the planet. Near Moscow is a much smaller body of water known as Lake Bezdonnoye, literally bottomless lake. Its reputation is far larger than the lake itself. Alexander Blok, one of Russia's best-known poets, recorded a local story that described the lake as an outlet of the world ocean. Over time, that image gathered more folklore around it. But the documented claim we can trace is the story Blok recorded, not physical evidence of an underground link. Another famous story says that chemist Dmitry Mendeleev tried to measure the lake with a weighted rope nearly 330 feet long and never touched bottom. It is an irresistible scene. One of history's great scientists in a small boat, lowering the rope foot by foot until none remains. There is only one problem. Documentary evidence confirming that experiment has not been established. The Mendeleev sounding survives as a local legend, not a verified scientific result. And the stories about an underground connection to the ocean have no credible geological support. But the legend contains a useful lesson, because a weight can fail to find solid ground even in a lake that is not exceptionally deep. Many small forest lakes accumulate organic sediment, decomposed plants, fine mud, peat, and suspended material. Instead of a clean boundary between water and rock, the lower part of the lake can become a gradual transition from open water to watery sediment to denser material. A light sounding weight may stop on the first resistant layer. A heavier one may pass through it. And if the sediment is deep and soft, the line may continue downward without the sharp impact expected from stone or sand. To the person holding the rope, it can feel as though the weight is falling into empty space. This is sometimes described as a false bottom. It is not a hidden portal. It is a measurement problem created by material that behaves partly like a liquid and partly like a solid. Lake Bezdonnoye therefore gives us two different stories. The folklore story connects a forest pond to the world ocean. The scientific story shows how easily a familiar tool can produce an unfamiliar result. The second story is less supernatural, but it is more useful, because it teaches us to question what an instrument is actually measuring. Now return to the forested opening in the Czech Republic. Hranice Abyss is not an ordinary cold water sinkhole. It belongs to a hydrothermal karst system. Groundwater moves through deep fractures, warms below the surface, absorbs large amounts of carbon dioxide, and rises through limestone. The carbon dioxide makes the water more effective at dissolving the rock. Instead of a cave being carved mainly by water descending from above, part of this system developed through chemically aggressive water moving upward from depth. Even the water temperature breaks the expected pattern. Hranice remains around 59 degrees Fahrenheit, warmer than the nearby river during much of the year. The cave's known geometry is the product of decades of exploration. Human divers pushed to extraordinary depths, but the environment imposes severe physiological and logistical limits. Several hundred feet below the surface, pressure changes breathing gases, compresses equipment, and turns any return to the surface into a long, carefully managed decompression process. Robots can avoid decompression sickness. They do not eliminate the geometry. In 2016, a tethered, remotely operated vehicle descended 1,325 feet below the water surface. The live video and commands traveled through its cable, but the tether also imposed a hard limit. When the available cable ended, the mapped cave ended with it. In August 2022, the UX-1 Neo autonomous underwater vehicle entered the abyss. Unlike a traditional ROV, it did not need a cable for real-time control. It carried multi-beam sonar, scanning sonar, 6 cameras, and structured light systems. It could estimate its own position and build a 3-dimensional model while moving through the cave. In only 2 days of missions, the robot mapped large sections of the flooded space and reached nearly 1,480 feet underwater. Again, the expedition stopped at a technological boundary rather than a confirmed geological endpoint. Add the dry chasm above the water, and the explored system extends more than 1,700 feet from the surface opening. But even that is not necessarily the full depth. Geophysical research has suggested that the underlying structure may continue beyond roughly 3,000 feet. That possibility has received enormous attention and scientific criticism. The important point is that a system extending more than half a mile beneath the surface remains an inference based on geology and geophysical signals, not a camera-confirmed measurement. Directly mapped underwater, nearly 1,480 feet. Potentially deeper, yes. Confirmed beyond half a mile, no. This is what responsible mystery looks like. The uncertainty remains, but the uncertainty is labeled. At nearly 1,480 feet, the surrounding pressure is roughly 660 pounds per square inch, about 45 times atmospheric pressure. Yet pressure is only one of the problems. A vehicle must know where it is inside an irregular shaft, avoid walls, distinguish open passage from misleading echoes, preserve enough energy to return, and maintain a reliable record of its route. In a straight ocean descent, down is obvious. Inside a cave, the deepest route may begin by going sideways. Stories about deep lakes sometimes describe mysterious zones where compasses spin and radio signals suddenly die. The real explanation is more interesting because it applies to almost every underwater mission. Ordinary radio communication works poorly through water. High-frequency radio signals that travel easily through air are rapidly absorbed below the surface. Very low frequencies can penetrate farther, but they carry little data and require specialized systems. That is why many ROVs remain connected to the surface by a tether. The cable provides power, sends commands down, and returns live video and sensor data. But a tether inside a cave behaves like a lifeline dragged through a maze. It can rub against rock, loop around a projection, create drag, or prevent the vehicle from entering a narrow turn. An autonomous vehicle has no cable, but that also means there is no continuous human control from the surface. Now the robot has to navigate for itself. Acoustic communication and sonar travel much farther through water than ordinary radio. Yet sound reflects from the surface, the bottom, and cave walls. Multiple echoes arrive at different times. Vehicle motion changes the signal. Bandwidth is limited, and a cave can turn one clean pulse into a confusing sequence of returns. So when a robot loses a clear signal in a flooded cave, the planet is not protecting a secret with a magnetic force field. The machine is confronting one of the hardest communication environments on Earth. There is a useful counterexample in northeastern Mexico. El Zacaton is a water-filled sinkhole with warm, sulfurous water and nearly vertical limestone walls. For years, human divers and lowered instruments could not establish its complete geometry. Then, in 2007, a NASA-funded robot called DepthX entered the water. DepthX was built as more than a remote camera. It was an autonomous explorer, a machine designed to enter an unknown three-dimensional space, map it, choose safe routes, and return without a tether. The technology also served as a testbed for future exploration of places where direct human control may be impossible, including subsurface oceans on other worlds. As DepthX descended through Zacaton, its sonar sensors measured the distance to the surrounding walls. Software combined those measurements with motion and depth data to construct a three-dimensional map in real time. This time, the robot found the flaw. The bottom slopes from roughly 1,035 to 1,050 feet below the water surface. A narrow feature may continue outward near the lowest area, but the main shaft was finally mapped from opening to bottom. Finding that flaw did not make Zacaton less extraordinary. It made the mystery more precise. The robot revealed the shape of a place no human could safely survey in the same way. It also collected biological material from the walls, including samples taken at depths approaching 890 feet. Those samples contained previously undocumented microbial diversity. The most important discovery was not a monster or a lost ship. It was life operating in warm, dark, chemically unusual water. A biological world that had been present all along, beyond ordinary observation. Zacaton demonstrates what happens when exploration technology finally overtakes a legend. The result is not disappointment, it is a better question. Once we know the depth, we can ask how the shaft formed, how water moves through it, and how life survives inside it. The lakes and flooded caves in this story are not truly infinite, but the word bottomless survives because it describes an experience. It is the moment when a rope ends before the sediment does. When a sonar beam enters a passage and returns no simple answer. When an ROV reaches the end of its tether. When an autonomous vehicle sees another opening, but calculates that it must turn back to return safely. Every generation draws a line beneath the water and calls it the known depth. Then a better instrument arrives and moves the line. At Serrik Kell, a hidden groundwater network supplies a lake with no large visible inlet, and a cave mapped to 915 feet appears to continue. At Lake Bezdonoye, Folklore turned an uncertain sounding into a tunnel to the ocean, while soft sediment offered a more realistic explanation. At Hranice Abyss, the mapped depth advanced from the limit of human divers to a 1,325-foot tethered robot, and then to a nearly 1,480-foot autonomous mission, with the deeper structure still unresolved. And at Zacaton, a robot finally found the bottom, drew the walls in 3 dimensions, and returned with evidence of life. The pattern is clear. The mystery is not that Earth forgot to build a floor. The mystery is that a lake can be only a small, visible entrance to a system extending through solid rock, a system shaped by chemistry, pressure, flowing water, and time. From the shore, the surface looks complete. Below it, the map may contain only a few confident lines surrounded by empty space. That empty space is not proof of the supernatural. It is an invitation to measure again. And somewhere beneath a calm blue surface, another robot will eventually switch on its lights, compare its position to the last known point, and move the edge of the map a little deeper. If you want more investigations into the hidden systems of our planet and the technology we use to reach them, subscribe to Frontiers of Reality, because the most extraordinary places on Earth are often not far away. They are simply below the last place we have been able to see.